Thank you very much for having me today. I would like to talk to you about surrogate models, which I think are building blocks of current industrial revolution. To explain this, I first need to define what digital twins are. So we define for industrial revolution. We started off by improving things using machines, steam. Then we moved on to electricity. We started benefiting from computers. That's the third industrial revolution. And now, building on that revolution, we have Industry 4.0, and we're hoping to automate everything from all the physical experiments to virtual world. And to make that happen, we need to construct digital twins. Now, I'm sure this concept is familiar to you. You've probably heard some definitions of a digital twin. However, they might differ slightly, and that depends on the expectations. But at the common denominator, at the core, a digital twin is always seen as a virtual representation of a physical system. So there's something that exists out there, typically a nuclear power plant, and we want to build a virtual representation of it so that we can perform all sorts of experiments, we can probe it, we can ask what-if questions, and hopefully we can use it throughout the life cycle of the physical product. Now, why this is important? Well, going back to that nuclear power plant, risk analysis, we want to be able to perform sophisticated studies of how certain systems perform under varying conditions. So, for example, if we know that the weather conditions will change, we might have certain gas leaks. We want to understand how that particular structure might behave. So, what do we need to do to fulfill the promise of a digital twin? There are multiple challenges, but people are advancing with enabling technologies. And today, I really would like to focus on the aspect of physical realism of digital twins, real-time modeling, and modeling under uncertainty, where there's lack of knowledge, there are errors, there's lack of accuracy. And that brings me to the next part of this presentation. It's focusing on modeling and simulation. I'd like to define two types of modeling. One is physics-based modeling. What do I understand by this? Well, we observe something, and we observe certain phenomena. We have some understanding of them, and we create models, a set of equations that allow us to obtain solutions that match the observations that we see. Now, because we don't necessarily want to solve ourselves this complex equation, we will discretize them and we'll ask the computers to do the job, so we'll have numerical solutions then. So in a way, this is what we can perform physics-based modeling for the physics that we know. Unfortunately, we don't have one unified equation. So depending on what scale we're working in, whether we're looking at atomistic scale or we're looking at macro scale, we have different set of equations, which means we have different solvers. And if we want to study more complex systems, we quite often need to couple these solvers to understand, for example, how a fluid and solid interact with each other. We'll need different set of equations for both. Now, there's this other aspect of modeling, which is data-driven modeling. Well, so what is this? In this case, we actually don't have a model.
Maybe you want to mute yourself, Tim, if you're going to sneeze.
Oh, sorry. That's what I had.
So in data-driven modeling, we don't have the model. We don't have these differential equations that describe what's happening. Instead, we have data sets. We have inputs and outputs. And what we do, we try to, through the use of data, we try to understand what's the relationship between those. So data-driven modeling is deriving the model from the data. And the simplest example is interpolation. We have pairs of inputs and outputs. We interpolate over them, and we can use that interpolator later to get more samples. So some people say that in a way, data-driven modeling allows us to observe not only non-physics, but also unknown physics. We're not constrained by the models that we construct ourselves, but rather the models are derived from the data. So there's a chance, there's something in the data that we don't know yet, but we're able to extract these patterns. And well, obviously, both there's no perfect world. Both of these approaches have advantages and disadvantages. For example, data-driven models, once trained, they're quite stable. However, physics-based modeling can generalize better within the same physics than the data-driven models. So ideally, what we would want is some kind of hybrid approach that benefits from the data-driven aspect, but also incorporates some notion of physics. And this is what I want to focus on today, and this is what I will call a physics-informed surrogate. So, surrogate modeling, the main subject of this presentation. So what are surrogates? Well, you can think of them as some kind of underlying function that describes relationship between inputs and outputs, but at the same time, it replaces something else, some other expensive simulator or expensive experiment. So that's the aspect that distinguishes it maybe from purely data-driven type approaches, because there is some other simulator that we could use. We could perform some expensive experiments, but for studies such as sensitivity analysis, optimization, we cannot afford having repeated experiments. Therefore, we're going down the route of constructing a surrogate that is some kind of approximation, but luckily allows us to obtain many samples at a lower cost. So yes, so that's the surrogate. We have some kind of design parameters. We have some outputs. There's a simulator, an experiment that generates these outputs, given these design parameters, and we want to replace it. We want to mimic it the best we can. So we're trying to balance the cost and the accuracy. And this is how we construct the surrogate to then be able to apply for calibration, to understand sensitivities of the models that we're analyzing, and also to augment the results. There are different types of surrogates, of course. So we mentioned interpolation. So we have these data fit type models. Interpolation means that the model for a given input matches exactly the output. That's the interpolation. And we can have some stochastic interpolation, that's Gaussian processes. But we also have other types of surrogates. We can talk about reduced order models. So for example, having a partial differential equations, we have some set of basis functions chosen carefully, and we can project our equations onto these basis functions. And by doing so, we might reduce the dimensionality of the problem. We also can look into hierarchical models. So if you're working with models that require grids, we can look at coarser grids, or we can simplify the physics. So in a way, by doing so, we're looking at some kind of approximate emulator of a more expensive high fidelity model. So going back to digital twins, where so why surrogates are important for digital twins, and why do I think that they play a role in our industrial revolution? Well, if we want really to have a digital twin that allows us to fully mimic the physical asset, allows us in real time analyze it, perform uncertainty studies, understand how to perform optimization, how to perform control. We need to be able to perform multiple experiments very quickly and accurately as much as possible. And this is where surrogate models come into place. Okay, so what I would like to do now is to basically give you an example of using surrogates for different tasks. The first application will be estimating uncertainty. The example that I'll show you is quite a typical study. So maybe nothing too exciting, but just wanted to give you an idea of what usually is being done when it comes to using surrogates for this kind of application. But later I will talk to you about project that I'm currently working on, and it's about predicting turbulence. And I would like to show you how surrogates can be used there. So, estimating uncertainty. There's a lot of uncertainty. There are a lot of errors, whether we're talking about an experiment or we're talking about computer models. And we want to be able to quantify them, understand how these uncertainties affect our outputs, our predictions. So we want to move away from deterministic analysis and work in this probabilistic realm. So as I mentioned, there are multiple uncertainties. They can be related to numerical errors, human errors, model form type errors, which are related to some missing physics or assumptions that we make. And how we can perform the quantification of this uncertainty. So if we have a model, could be an experiment, we have some inputs. There's a parameter that goes into that model, and afterwards, when we execute that model, we obtain an output, we obtain a prediction. Now that's a deterministic approach. I have one value, and for that value, I'm getting one output. What we like instead now is to accept that we don't have a fixed value for the parameter, but rather we have a random variable. And this random variable has a probability density function. And therefore, it can accept values depending on that density function. And when I propagate that PDF through the model, I will then end up having some more statistics on how the outputs are affected by the fact that the input might accept different values at a different probability. So I can obtain the mean, the variance, and I can do that because my outputs become random variables as well. So they have a probability density function. We can also perform an inverse analysis. So what it means is if I have some outputs and I have some observational, some new observed data, I can then maybe perform a backward analysis and understand what's actually is the input probability of my parameters. So I'll be more confident about the inputs that I'm using. So that's the example of performing a certain quantification for an elliptic PDE with random coefficients. So this is a diffusion. This is a diffusion model. Basically, imagine that you have a piece of material, right? That material can have different heat conductivity, and we want to understand how temperature dissipates for that material. So we have some kind of source, that's F. In here, that's the F, that's the source. U in this case really can be temperature, and A will be our diffusion coefficient, which is related to the conductivity of the material. Now, we can assume that the material is homogeneous, right? So at each point of that material, we have the same conductivity. In real life, lots of these kind of things are rarely homogeneous. There are variances. But we don't know exactly what these variances are. So what we end up with is some kind of, I'm getting confused with the computers, some kind of a random field, which means that at each point, we don't know exactly what the value of conductivity is, and therefore we can accept that at each point we have some kind of a distribution of possible values. So a random field is a collection of random variables. Luckily, we can work with this, and if we define a mean and a covariance, we can actually construct different realizations of this random field, and for these realizations, we can perform simulations. So that's great. Well, not quite, because it's still infinite. So we have infinite number of random parameters that define a stochastic field. But usually what people do, they perform the Karpman-Loew expansion, and they don't work with infinity, but just say we're going to truncate at some n, and we're going to construct our random field by summing up some basis functions that are related to the covariance of the stochastic field. They will be weighted, and we'll add this to the mean, and we'll have some realization of our random variable, of our random field. There are other things to do that as well. But one key assumption here is, in this case, we want, for example, A to be bounded. We want it to be positive. If it's material, we don't want these conductivities to be negative. Okay, so we don't want to work with random variables anymore. We want to talk about parameters. The reason why we talk about parameters, so in this case, it's noted that there's no omega, but we work with y, which is an image of a random variable, because this allows us to introduce this probability measure, which is probability density function. So now we're working with y's, and there's n number of y's that construct this random field. And each of these y's have a density function from which we are going to sample. So it's still quite an expensive study to do. But obviously we don't want to do it by hand, so we'll need to discretize it. And there are different ways to do it. Let's use finite element method. And the two essential steps to perform finite element method is to rephrase our problem in a weak sense, and then discretize it in a finite dimensional space. So this is a reformulation of the problem in a weak sense. So notice, look at that brackets here. So this is the inner product. So we have some kind of v here. That's our test function. It's an arbitrary test function, and we're calculating the integral of product of this test function with our PD, and that's the weak form. Why do we work with the weak form? Because it relaxes some of the constraints and remove second derivatives. So it's just easier to compute this. And now that we have the weak form, we can then move on and discretize our problem, which in this case is quite simple. We don't work with U, we work with UH, and UH is an approximation. Again, it's a sum of some kind of weighted functions, and these could be hat functions that are related to the nodes of our domain. And that's pretty much it. But that's just discretization of the space. Now we also have the parameter space that we need to discretize. So we need to be able to calculate this for the different values of y's. So what we're going to do, well, we can either work with Monte Carlo, so execute this finite elements solver that we just constructed for hundreds and hundreds of values of y, or we can use stochastic collocation, which in this case will be basically representing our problem as, again, sum of some kind of basis functions, in this case, polynomials, particular polynomials, Lagrange polynomials. And for different values of y's, we obtain the solutions that we use as coefficients that we weight our polynomials with. And if we introduce that into our solver with only a certain small number of runs, we can actually have quite a good approximation how our temperature is affected by the fact that it might be traveling through a material that can have all sorts of different conductivities with only a finite number of executions of the solver. So now the other project that I wanted to talk to you about, so that's predicting turbulence. Here there will be a little bit more novelty. Neural networks. I think neural networks is a popular subject. I thought I would start with it. So neural networks is a data-driven model. On its own, it has no understanding of physics whatsoever. It only works with data, right? It's a very expensive interpolator, but it's a very useful one because it performs in a high-dimensional space. So what it consists of, we have a certain number of nodes. Each of these nodes contains some kind of activation function that introduces nonlinearity into our study. We have connections to nodes that belong to another layer. Each of these connections are defined by weights. They basically tell us how important is that relationship. So if the information passes through that connection, it might be, if it's small, then it might not be, not much information can be communicated. If it's large, it will be heightened. Okay, and so basically usually we start with fully connected network, which means we assume that all of them are important, and during the training, some of these connections can vanish. So we have more sparse connectivity. So each node accepts inputs from the previous nodes, which are basically multiplied by these weights. They have bias added to them, And all of this goes as an input to an activation function. Here. So, like I said, this is just a data-driven model. So it will only try to if it's supervised learning. So we know what outputs should be. It will only perform a kind of interpolation for us. But we realized, or people have realized that, well, during backpropagation that you do while you're training your model, you actually calculate derivatives of your loss function with respect to the parameters that we saw before. And having these derivatives, we can actually incorporate a bit of physics into it, because we can, if we're working on the data that comes from a non-physical model, we can see whether the outputs that we're obtaining are fulfilling that particular partial differential equation. And that's one of the ways how people are incorporating physics into neural networks. So what they do, instead of only having a loss function related to how far my prediction is from expected output, we can have additional loss, which says how well these derivatives or these solutions solve the partial differential equation that I have at hand. So these ideas actually came from fluid dynamics community, and there's a good reason for it. Understanding fluid dynamics is very important for many areas. Unfortunately, the tools that we have are very expensive to use. So computational fluid dynamics tends to solve Navier-Stokes equations, which for real-world problems is just impossible to solve. It's too computationally intensive, and we work with all sorts of approximations. So neural networks seems like a way to maybe accelerate some of the computations that we're doing. So one of the things that we've been looking at is so-called zero-shot super resolution. What do we mean by this is that, how about we solve Navier-Stokes, but at a low resolution that you see above here. And we use neural networks with some physics in it to super resolve it. So instead of having this, in the end, we have all the detailed information about the flow. So it's like as if we executed Navier-Stokes solver for a very high resolution, but at a lower cost. And zero shot, because we will never show to the network the high resolution. It will only work with the low resolution. The reason why we won't have to do it is because we will give it some information about the physics. So the mathematical model, that's our two-dimensional Navier-Stokes equation. It's problematic, particularly because of that pressure that you have here. It's quite expensive to compute, and we often have to solve another set of equations, quantum equations, to obtain it. On top of this, it's a mathematical model for a deterministic chaos, which means that if we don't know exactly the forcing and we don't know exactly the initial conditions, we will never be able to predict what's going to happen with the system. So we have to be very careful when we're using these kind of models. So what we're going to do is we're going to assume that we're working with observations Y, that take these high resolution inputs, project them onto low resolution, and we'll add some noise to it to make it more interesting. And these are the observations that we have that we can work with. And we'll try to use them while we're solving our Navier-Stokes equations to then super resolve the solutions. And so what we will do, here I'm just explaining that the projection onto lower resolution is basically just averaging over squares, just to make it easier. So now you see this is the Navier-Stokes equations that we had, but instead of but the difference here is that we have the Z. Z is something that will try to approximate the solution of Navier-Stokes equations. So in time, it will try to get as close as possible to the real solution. We'll help it because we'll add this additional term here, which is F. We call it an innovation term. And what it does, it fits in our low resolution data. And it will try to and it will project it onto the higher resolution grid and see if this can help teach set to match the high resolution Navier-Stokes solution. So after discretizing our equations, we then are still having the issue of the pressure and the forcing. Unfortunately, like I said, if the forcing is not quite right, this whole idea falls apart. Pressure is a problematic thing because we need to solve another set of equations, it's expensive. So here we're going to use neural networks. What we'll do at a given time, we're going to feed a current Z to the neural network, and we'll ask it to give us back the sum of the forcing and the pressure gradients. And this will help us to propagate the solution to the next time. And here are some of the results. Gamma here is related to the innovation term that you saw here. So all it's doing is just increasing or reducing the influence of the data that's coming in. So the higher gamma, the more important the data is. And what we're seeing here is that from the low resolution data, we were able to reconstruct the true solution. And over time, we were also able to predict what's going to happen to the system at time t+1. So that was, we're quite happy with this, but there's still a lot to work on. So if, for example, what we're going to do when data is very heavily corrupted with noise, and this is currently what we're working on. We want to take a very noisy data, obtain only low resolution from it, and try to predict what should be the high resolution field. These are just recent results. It seems like it's kind of working, but there's still a lot to be done. Okay, so these are just final thoughts. Really, what I wanted to say here is that modeling in general is very important, and data models are very useful as well as physics-based models. I don't think we can just fully rely on one or the other. We really should look into some kind of hybrid approaches, and we do have to have understanding of the application area that we're working with, because that additional injection of information can accelerate the analysis. Okay, thank you so much for your attention.
Great, thanks so much for that. So I think what we'll do is we'll start with questions in the room. So I'll be the usher, kind of handing the microphone out. So if you've got a question, I'll come to you, just kind of introduce yourself, and then I'll hand the microphone back to Maggie. So yeah, questions in the room first, then we'll go online. Yep. Okay.
Oh God, that's that code. You mentioned like you preferred stochastic models over like Monte Carlo models. Is there any particular reason for that?
Whether I prefer, sorry, let me double check if I understood correctly. You're asking whether I prefer stochastic models over Monte Carlo?
Yeah, it's in the presentation.
Yes.
Sounded like that.
Oh, I see. So no, Monte Carlo is still a golden standard when you're performing stochastic analysis, and we'll never leave it behind. It's particularly useful when you're doing when you're working with high dimensional problems. It's been shown that Monte Carlo is independent of dimensionality of the problem, and therefore it will be equally expensive for low dimensional problem as it is for high dimensional problem, which means that for low dimensional problems it's a bit of an overkill. So if you can look into other methods, that's probably preferable. Thank you.
Great, thank you. Okay, I've got a bunch, so I'll start with one. Okay, so you started off by talking about different sources of uncertainty. We had like that big kind of tree showing kind of different areas. So I was wondering, do you kind of treat all those like independently? Like, do you have different methods to deal with different sources of uncertainty? Are there any sources of uncertainty that are particularly hard to deal with in different areas?
Thank you. Yes, so quite often when you perform uncertainty quantification study, you'll see that people try to understand how input parameters are affecting outputs. It's much more tricky to try to quantify how our assumptions in model form parameters affect our solutions. So, for example, if I simplify physics, how is that affecting the predictions I'm making? So apart from comparing it to observations, it's quite difficult to set up the right experiments to look into this. So that will be a tricky thing. And obviously, when you don't have any way to describe the uncertainty, usually what we do, if we know nothing, it's probably Gaussian. But it's just a guess, and it has an uncertainty in it as well. So if there's no information that can somehow constrain the problem, that's problematic. Otherwise, there are lots of tools out there, and all of them can be good depending on the setting.
Any other questions in the room?
Hi, sorry, I'm Chris. You were talking about, forgive me, I can't remember the exact term you used, but effectively neural net upscaling of data.
Yes.
So one thing I can't quite wrap my head around is you're effectively throwing away information by rendering it a lower resolution.
Yes.
And then using a neural net to re-render a higher resolution copy.
Mm-hmm.
However, by going to a lower resolution and throwing away data, surely that would mean that you have effectively a degenerate problem where multiple different states could replicate that lower resolution copy. And then obviously using the same neural net on that lower resolution, you're going to end up with only ever one result. Are there any mitigations to that?
Thank you. So like you said, this kind of super resolution is ill-posed, right? So you're very right about this. The reason why we're able to upscale the data is because we have understanding of the physics. So we embed our partial differential equations into the network architecture. If we didn't do it, it's nothing good. So there's this additional information that you provide. Without this, it's impossible. So I did also, so I use this kind of analysis for just filtering the data to see if I introduce some information about the physics, can I filter better than just applying kind of a black box approaches? I don't know, whether filtering. And you always do better when you provide more information. And that's it. This is this additional constraint that allows you to reverse irreversible in some sense.
So is there only one solution then? Like, you know, if you were to go from low resolution and upscale it, is there only ever one possible upscale solution to that?
So it depends on how much constrain it. Unfortunately, if your constraints are not very strict, then no, and there's not just one solution. It might be that, you know, if you take a flow field, right, that comes from from solving Navier-Stokes equation with a particular viscosity, so a particular Reynolds number. If you obtain a low resolution from it, it might just happen that the low resolution will look the same for different Reynolds numbers. And unless you provide an additional constraint, you probably can't fight it.
Thank you.
I follow the trend of the questions.
Sorry.
So if you're comparing a high resolution solution for the solution of Navier-Stokes and one of the super resolution, do you find some frequent data? So you are the differences between the real simulation and the super resolution simulation are always comparable. You always lose some key features of the fluid, like resolution of knots of eddies, or some simulation does better, the neural network does better in other things. If you have investigated this research.
Well, so in this case, we were actually quite successful in reconstructing the data that we had. but then bear in mind it was two-dimensional. So then there are certain flow structures that we would not observe in 2D. I don't know how well it would perform in 3D. I would think that in this kind of super resolution studies, the most difficult is to reconstruct small scale features, because they're often lost completely when you perform this averaging. So these small scale features you cannot recover unless you have some understanding of the system that you're solving, and how well you teach the network to be able to predict these small scale features, seeing only larger features. That's probably the most tricky. So the small scale features is what you lose the most. And if you have a good architecture that is able to super resolve the data, if it's able to resolve the small scale features, I would consider it as a successful methodology. But we only tested on 2D, so God knows what happens in 3D.
Yeah, on that, could you go back to the slide where you show the error for the neural net, the Navier-Stokes problem? Yeah, this one. Yeah. So yeah, how are you computing relative error there? Is it just sort of pixel difference averaged over the?
Yeah. Yeah, so in this case, it's just a relative error, which is the difference. It's a norm of the difference between the ground truth and what we estimated over the norm of the ground truth. So it's just by points in this case. And what we're trying to show here is because someone can say, well, I can take the pixelated image that we see here and try to interpolate. So use cubic spline to interpolate over and obtain the higher resolution. So what we're trying to show here is, so that's the result that we would obtain. That's the black line here. And we managed to get something that's better. And so that means we learn some physics. When you do interpolation, it's a black box. So you're just working the data. So there's nothing more you can do. So without the physics, you won't be able to go below this. And we're showing that there's a way to incorporate physics, for example, in this way, and you're able to improve on your predictions.
Okay, so have you tried just plotting, say, gamma equals 100 divided by true, and just seeing if any like interesting features come out, like, you know, maybe error is concentrated more in certain areas than others? So I mean here we're dividing by the norm of the ground truth. So that's the relative error. In terms of, so you're wondering whether there are certain areas that are less less well predicted. In this case, because it is quite even though it's Navier-Stokes is difficult, it's still a model problem. So the highest error will always be when there are small scales. So this is what we discussed. So whenever you see a blob, I'm pretty sure we're doing quite well where there's a blob. But where there are some small scale features, notice that, for example, I don't know if it's visible here, but there are little things going on here, and they're almost lost in this low resolution image. So then if you're able to resolve this, that's pretty good. So probably if there's an error, it's concentrated more in these areas where there are small scale features. When you have larger features, because you have some information of them in low resolution, because these are these low frequencies, it's easier to reconstruct them. So I'm not hogging all the questions. Has anyone else in the room got a question? Yeah.
In the earlier part of your talk, you mentioned how the digital twins could be used to find good work regardless of unknown physics. Would there be a way of extracting the unknown physics back from the model?
Okay, I just want to check if I understood. So you're wondering how we can inject this unknown physics back into the model that we learn from the data.
If you find that a model works, suggests unknown physics, is there a way? Because one of the main criticisms of machine learning is that it's often a black box. Is there a way of been looking into ways that we could extract the physical rules that it's worked out back from the system?
So this is a complicated question. So first of all, like you said, it's a criticism of machine learning in general, because we don't trust what's coming out of it. If we don't know the physics and it's showing us something that we've never seen, now is it just a made up thing, an error in training, or it's really something new? And one way to do that, one way to maybe gain a bit more confidence in machine learning is to work with probabilities. So not ask for one precise number, but give some kind of a distribution of possible outcomes to tell us, so that the model can tell us how sure it is about how well it did as well. So there are some ways to go around this way. You can't avoid using real data. So unless you find some kind of observations, experimental observations that can match whatever is coming out of the model, you can't be 100% sure that this is a new unknown physics that's been discovered. So you will always need to have some kind of confirmation in the experiment. About injecting it back into models, I think it's all about patterns. So so you were wondering how we can, did I understand correctly, how we can construct a model based on what the machine learning came up with and use it? Is that what you were asking? So you know, if we think of machine learning as an interpolation, so that's basically, after training, we can just use it to generate all sorts of data for us afterwards. We can give it a new set of inputs, and it will work like any other simulator or model. It will produce predictions. We just might not know exactly what the structure of it is, because it's all hidden, and that's the biggest issue. But we will get output, so we can use it, and therefore, it will become some kind of like a multi-dimensional interpolator, and we can plug it into, also to connect it with other models, and it's just a matter of transferring the data. So this is how you can use it. It's just a question of, we don't know what that model, we don't have a proper, apart from these matrices of parameters that we trained, we don't really know the model that it created. So this is the tricky part.
So on that, I think, at least in astronomy, I'm aware of some people who try to take like the orbits of planets and stuff like that, and then just using that as data, see if they can extract the law of the laws of gravity from that. I think it's sort of like using basis polynomials and things like that for your model. You have like a library of kind of functions, polynomials, sines, whatever, kind of going into it, and you find which ones work best. And sometimes you do extract the truth. You do kind of, you know, get Newton back out again. So I think it's still quite a young field, but people are interested in using it for things like modified gravity, you know, for things like that. You know, if I don't assume there's dark matter and I just see that there's stars and gas and stuff like that, what law of gravity does my model can spit out? I think it's still quite a young field, but definitely an interesting one. Okay, are there any other questions in the room? Yeah. Great.
So when you were doing testing of the models, did you find sort of any limits on the resolution? So is there a sort of a lowest resolution beyond which you cannot then scale up and get accurate results? And also, is there a sort of a level of high enough resolution where it starts to become inaccurate again?
Yes, of course. There's you cannot go below certain resolution, and it's very much problem dependent. So there's no one fixed answer, but obviously there's this zone. So when you reduce dimensional, so when you create a low resolution, you lose accuracy. But for example, when you average, so we obtain low resolution by performing square averaging. When you do square averaging and you say that your noise, that your data was corrupted with white noise, you actually remove some noise, so you perform filtering. So there's a balance between filtering and a loss of accuracy. So there's a sweet spot somewhere there. And yes, below certain resolution, there's not much you can do, because you just lose so much information that you even introducing some partial differential equations into your network architecture will not help, because you just don't have enough information. In our case, the lowest resolution that we considered was 16 by 16 squares. It would not work for less than that. But this is just an very empirical results. We're working on the theory that can give us some kind of constraints, depending on the type of operation that you use for obtaining low resolution, and how much gain you have using these kind of state estimators. So we're working on the theory. At the moment, it's just an empirical result.
Any more for any more? Okay, should we open up to online then? So if you're dialing in from home, you want to just kind of shout us a question, feel free. Otherwise, put it in the chat and I'll read it out. Okay, Aravinda.
Oh, hi. I just had a question about the or two questions actually. One, I'm not sure I understood what the gamma was, but is there a, so it seems to me that the higher the gamma is, the better the error is on this plot on the screen. Is there a cost to increasing the gamma in this way, or is it just an optimum?
Right. So there's no cost to it. So I'll explain a little bit more what gamma is, so that it's easier to understand its influence. So basically, if you look at these equations, if you don't consider f, it's your Navier-Stokes. We are adding this additional term that we call innovation term. And what is this is gamma times the projection operator, and then our low resolution data minus projection operator onto the current estimation of the state of the system. So our equations give us the current state of the system. We project it to low resolution. We subtract it from our observation data, project everything onto higher resolution, and then multiply it by gamma. So gamma is just a number, a way that tells us how important that difference, how important is the data, that observational data that we consider. So in this case, because we have nice, not much noise data, then the more we consider it, probably the better, because it provides more information. It provides like a correction term for the training. But if you imagine that you have noisy data, if the value of gamma is high, then you amplify the noise. So then the situation will be different. So it's not always given that the highest value of gamma is the best. It's the kind of parameter that you will have to, that should be a function of the setting of your problem.
Okay, thank you. That makes sense. Just the second question was, I see that even with, so maybe with gamma equals 100, that there's almost a flat evolution of the error with time over 5 time steps. I guess the aim of this is eventually to kind of start replacing simulation-based models. I know you said it's early days, but has there been any kind of work towards slotting this in between time steps of a simulation and seeing if you can integrate it into a simulation as an intermediate step or something like that?
So for this particular study, at the moment, what I'm looking into is trying to see what happens if I obtain data from different solvers, because different solvers will carry different numerical errors, and I'm just looking into how that affects the performance of this kind of training. But I haven't yet coupled it with a solver and run it in real time. Although, actually, no, for this experiment, in some sense I did, even though it was done in a post-processing. But while I was training, I was providing it data. It's just I had data sitting on the computer. But it's not a problem to just have a solver that produces that data running on a different node and let the data stream. It was just easier for me to reproduce the experiments, but it can be done. So basically, we are already at the stage that if you have 2D Navier-Stokes equations that were solved on a low resolution grid, will most likely be able to super resolve it. But as I said, I don't know what's going to happen with 3 dimensions or if you have noisy data. But usually in computational fluid dynamics, there's no noise per se. There might be some numerical errors, but
Thanks.
thank you.
Okay, do you have any more questions online? Okay, if not, any more from the room? Okay, so I'll give you a last one then. So you've been, out of, I suppose, like a conventional academic research path for a while, like a post PhD. So I just wondering, sort of, how do you sort of reflect on the differences between conducting sort of academic research in like an industrial context as opposed to a university one? What are the upsides? Are there any downsides? Because the grass always looks greener from our perspective.
Yeah, so I try to keep contact with keep in touch with academic research. So I do work with mainly University of Manchester. So hopefully I still have some understanding of academic research. And one of the differences that I noticed was that in industrial research, well, I don't know if it's actually a difference. It seems like we're all bounded by where funding comes from, and academic research unfortunately suffers from that as well. So there are certain fashions in research. It's easier to get grants if you mention the right words. And it's true for academic research, and the same is for industry. Industry has its goals, and they want your research work and research output to somehow help them, fulfill these goals. And so there are these constraints. But one main thing that maybe differs from academic research is that in industry, it's required from researchers to be quite flexible, which means that it's harder to become an expert in a certain area, because it might be that you suddenly will have to switch your focus. And if you switch your focus too often, it's impossible to be an expert. You might just know enough to conduct a project, but not enough to be the person that teaches others. So I would say this is a little harder, and it requires knowing how to navigate the waters. If you want to spend if you have some kind of project that really is of interest, area that's of interest, and you want to grow in this area, or find the ways to make this relevant to the industry. So that requires a bit of stretching. So I would say that's the main difference. If you don't mind switching contexts, I think it's not so different from academic research. But if you prefer to focus on one particular area and you want to really grow expertise in it over many years, it's a little harder to do it in the industry.
That's great, thank you.